Okay, today we're going to talk about the first law of thermodynamics, in which it states that energy is conserved and that all energy turns into another form of energy but does not disappear. The example I use today is the M107. It's a 50 caliber long-range sniper rifle. It has a muzzle velocity of 2,800 feet per second and shoots a 660 grain bullet. This gives it an effective range of 1.8 kilometers and a maximum range of 6.8. Calculate the muzzle energy of the bullet. How high could the amount of energy carried by the bullet lift a 100 kilogram mass? How much would the temperature of 1 kilogram of water be raised by this much energy? There are two conversion factors necessary to do this calculation. The first is that 1 grain is equal to 64 milligrams, and that 1 inch is exactly equal to 2.54 centimeters. In this line, I convert the mass of the bullet into kilograms. So we use 660 grains times 64 milligrams per grain. Divide by 1,000, it gives us grams. Divide by 1,000 again, it gives us kilograms. Here we have the velocity of the bullet in feet per second, and I use all the appropriate conversion factors to convert it to meters per second. Why? Because we have to enter kilograms and meters per second into the formula for kinetic energy. We enter those values into the formula. Notice how when we square the number, we also square the units, so the meters become squared, the seconds become squared, so the final units are kilogram meters squared per second squared. We discussed in the last lecture that these base units give us joules. So the bullet moving at 2,800 feet per second, weighing about 42 grams, has 15,000 joules of energy. Now, using the potential energy formula, and that equals mass times gravity times height, we find that a 100 kilogram mass could be lifted to a height of almost 16 meters by the energy carried by the bullet. So a bullet weighing 42 grams and traveling at 2,800 feet per second carries enough energy to raise a 220-pound mass to a height of 16 meters. Now the same amount of energy as is carried by this high-powered rifle bullet could, if applied to heating water, raise the temperature of a liter of water by 3.7 degrees Celsius. How do we find that out? Well, we use the flux formula for heat. Q is equal to mc delta T, where Q is the heat flux, or the amount of energy transferred, M is the mass, and C is the specific heat capacity of the substance being that is receiving the heat energy, in this case water. So how much energy, so the specific heat capacity is how much energy 1 gram of something will absorb before increasing in temperature by 1 degree Celsius. And of course, delta T is the change in temperature. So we plug in all the values, 1,000 grams of water, the specific heat capacity of water, and incidentally, water has the highest specific heat capacity of any substance. The change in temperature is what we're looking for, so we rearrange the equation, and we obtain a value of 3.7 degrees. Mind you, the bullet doesn't do any of these things, so what is the point of doing this calculation? Well, it's to drive home the idea that the energy carried by the bullet has to be dissipated in some way, and it doesn't just evaporate. Where does the energy go? Well, some of the energy is turned into heat because of the jostling of air molecules. The bullet violently pushes aside as it flies to its target. Also, pushing the molecules aside takes work. So the bullet does mechanical work in pushing the air out of the way, and it also heats up the air that it pushes aside. Some of the mechanical energy is used to damage the target and to deform the bullet, and also to make the sound. So in conclusion, the law of conservation of energy states that any chemical or physical process occurs with transfers of energy. The energy changes form, but it does not disappear. Now let's look at something a little less dangerous than a bullet, a glass of milk. A glass of milk contains about 100 calories of food energy. How high would this lift a 100 kilogram mass? So first of all, we convert dietary calories into joules. The appropriate conversion factor is 4,184 joules per calorie. So we get 418,400 joules of energy in a glass of milk. The nutritive value of milk stores potential energy which can be released by the body's metabolism. Obviously, you can't load a glass of milk into a rifle, but you can drink a glass of milk, and then the energy that it gives you will allow you to do a certain amount of work based on how well your body digests the content of the milk. So again, we use that same formula. Potential energy is equal to mass times gravity times height. This is how much energy in joules is contained by the glass of milk. Here's our 100 kilogram mass. Acceleration due to gravity, we're solving for h. So we rearrange the formula. We find out that the energy contained in a glass of milk will raise a 100 kilogram mass to a height of 426.5 meters. So that's essentially enough energy to raise a 220 pound mass to the height, almost to the height of the CN Tower. So now let's continue our discussion of potential energy. A couple more terms need to be defined. First of all, potential energy. We keep on talking about potential energy. What is potential energy? It's the energy that an object possesses by virtue of its position or chemical composition. So we have this formula, potential energy is equal to mass times gravity times height in physics. And potential usually has to do with moving things against a gravitational or a magnetic or an electrostatic field. For example, if I raise this stapler, I'm doing work against the gravitational field. So now the stapler has a higher potential energy. If I were to let it go, it would crash to the countertop and make noise and potentially damage the stapler because of the work I did in lifting it, being released suddenly. You could also do work against a magnetic field or an electrostatic field, or with stretching and compression of elastic objects and substances. For example, if you compress air, you have to do work to compress the air. You're putting energy into it. Now the compressed object has potential energy. In chemistry, the potential energy of substances is released when bonds are broken. And of course, you put the energy into them when you make the bonds. The two words we should know about are system and surroundings. A system includes molecules we want to study, and the surroundings is everything else around it. And the conversion of energy. Energy can be converted from one type to another. For example, a cyclist has potential energy at the top of the hill and kinetic energy at the bottom. And in a chemical reaction, that same analogy can be applied to forming a substance where the bonds, as the bonds form, they capture a certain amount of potential energy, and those bonds can then be broken at a later time to release that energy again. So for example, when we make dynamite, we mix a certain number of ingredients, we boil the ingredients for a long time, and as the dynamite molecules form, they capture the energy of either the high energy ingredients that are used to make it, or the energy of the boiling to form this new substance, trinitrotoluene, which is highly explosive. It releases its energy suddenly, which is what it's useful for. In thermodynamics, the first law states that energy only changes form. It is not created or destroyed. When a system loses energy, it has been transferred to the surroundings. So this value E, which is called internal energy, is positive if energy is gained from the surroundings, and is negative if the system loses it to the surroundings. So when the system loses energy, it's called an exergonic reaction. When the system gains energy, it's called endergonic reaction. The change in internal energy is the difference between the internal energy of the products minus the reactants, or the energy final minus the energy initial. And internal energy is made up of heat and work. So whenever a chemical reaction takes place, as we mentioned in the last lecture, it releases a mixture of heat and the potential to do mechanical work. It's good to remember the sign conventions. Q, W, and E, the heat flux, the work, and the internal energy are positive if there's a gain of heat, if it's endothermic, or if work is done on the system, or if the system gains a total. If these two things add up to a positive amount, then the system gains energy. On the other hand, if the system loses heat, or if work is done by the system on the surroundings, or if these two quantities add up to a negative number, then energy, the net loss of energy by the system is indicated by a negative sign. It's interesting to point out that engineers have the conventions reversed. So when engineers and chemists get together, it can cause some serious confusion in the discussions.